Thanks everybody for joining, and this is going to be the first studio, what is going to be a new format of the Ataxia Global Initiative, the AGI. And my name is Matthis from the University of Tübingen. I'm part of the leading team of the AGI. As the AGI, we thought to introduce this new format, and it's also at the same time a new offer for all of you and your colleagues to contribute to this format, not just to be an attendee, but also to be a host, and maybe host is a similar format or studio as we are doing today in the next two sessions. So what is the format about? The format is called the Tools and Methods Studios. And we rephrased it from workshop because the term workshop is very inflationary used in science. Very often it's not a workshop, but a series of polished talks. We, however, really want to make this series studios, in German Werkstatt, where you really get your hands dirty. And just to introduce it to the concept, what is it about? The studio series are joint work studios with the aim to discuss and improve trial readiness tools and methods with regard to the novel or improved application in the ataxia field. So it's a work studio about trial readiness tools and methods. So it's only about trial readiness. It will neither be about clinical results per se. It will not be about basic science. It will not be about whatever. It will be everything should be related to trial readiness, and it's about tools and methods. So as opposed to, let's say, fixed results or fixed results presentations or project presentation, it's really about tools and methods. And why do we think so? Why do we think we need this? Because I think we all have it in the trial readiness field. There is a big bunch of methods and tools. Oh, first of all, there's a big series of problems and challenges we need to face. And what we're thinking is let's discuss methods on how to approach these problems and challenges, knowing that maybe none of the methods is perfect, or maybe even different methods would work. But we should, as a AGI, as a trial readiness ataxia field, we should come into terms on how to address problems and what might be good or not good methods to pursue forward. So it's really about advanced method discussion and it's hands-on work to debate and develop, tackle timely and hard to crack questions in ataxia trial readiness. So it's getting your hands dirty, like you see in the car repair shop up there. We are working here. It's a work in progress. We will not present a clean solution nor a recipe. Also, if you expect a talk, a webinar, or education series, this series will not be for you. Also, if you expect a polished overview, results, or nice introduction to the background, you can go have a coffee. This format is not going for you. It's work in progress, getting your hands dirty. The format will be quite standardized. It will always be 1 hour Zoom meetings with an intensive work discussion character. We are sitting together here in a work studio. And this is about 20 minutes input talk followed by 40 minutes of discussion. So you see the big bunch of discussion that's coming up. Today, the input talk is from Rummey. The number of meetings, so of sessions of each studio, can depend on as required. For example, one studio can have 1 meeting, it can have 2 meetings, or if we see that we need more meetings, we can have 3, 4, 5, or 6 meetings as required by the topic. Also, the cadence of the studio dates and the repetitions per studio is as required. So it can be kept dynamic, flexible, and open. So for example, you can have 2 and 3 in a row. For example, in this studio session, we have 3 sessions in a row. Then you can have a break and say, come on, we need a 4th one or maybe a 5th one as required by the topic. Who are the audience? The audience is cross AGI, everybody who is interested in, but again, it's not an introduction seminar. It's also not an overview seminar. Who can trigger a topic where you think, oh, that is a challenge where we need to discuss methods and tools? That would be the appropriate topics in the terms of ataxia trial readiness. Those topics can be triggered by any AGI working groups, members or AGI working groups. So for example, if and see James names on and others on the call, if you guys have a problem where you think this should be discussed methodologically AGI-wide, please propose it. The organization of those studios will be run by the AGI office. So this is the format. So it's a little bit unorthodox. It's nothing we are very used to in academia, but this is why we would like to kick this off and make it a new format. And the first studio we're going to have has the overarching title, Longitudinal Progression Modeling of COAs, so clinical outcome assessments in degenerative ataxias, differential value versus limitation of different models, namely of slope models as well as of change models, and those will be exemplified for degenerative ataxias. In this studio, we're going to have three input presenters. The first one today being Christian Rummey. Next Friday, it's Dieter Hilgers from University of Aachen. And in 2 weeks Friday, it's Sophie Tizenas from Paris. And the reason why we haven't given each of those three presentations a different talk, because it's not really like a fixed presentation title. It is their perspectives of the respective speakers to give their perspective on those models and what they think, what they can do, what they cannot do, and on their experience with using those models in existing data sets. So it's really more their perspective, their discussion input, rather than a fixed project title. So this is the session, and please, if you like the session today, feel free to register for session number 2 and session number 3. And we squeezed this in before the summer break because we wanted to have this triad or this trial session still done before the summer hits in. And what we might see, if we need a meta discussion afterwards, we might go for a session 4, which will then be after the summer break. We are already envisioning a second studio series, which is still in the planning phase, but which might be kicked off in fall, so let's say after the summer break in September. And that is the topic what Rebecca Schüler from Tübingen has proposed, also with Sophie Tizenas. It's going to be entitled Optimizing Ataxia Clinical Outcome Measures According to Patient Meaningfulness. So how can we optimize them on the one hand to sensitivity to change, but on the other hand to patient meaningfulness? So just stay tuned for this second studio series coming up in fall. With this, I want to close, and I would like to welcome Christian Rummey from the Clinical Data Science in Basel, Switzerland. And Christian is going to give us his perspective on longitudinal progression modeling of clinical outcome measures in degenerative ataxias. Thank you.
Thank you, Matthis. I also thanks for setting up that forum. I find this a really great idea. It's not too often that you get to discuss these kind of methods in such a group. So really great idea. I keep this as non-statistical as possible and try to make it really illustrative so that everyone can discuss this. You know what people do usually when they have to talk about people start to grab things from their history, and I thought we should use a clinical trial to show the different methodologies in these two analyses, change analysis versus slope analysis. And there's not so many trials in ataxia out there, especially none where I have the full data set of and spend like several years of my life working on. So this is a trial on respiratory function in Duchenne Muscular Dystrophy. So it's close, but it's not a degenerative ataxia. So I want to mention that this trial was also based on natural history data. So it was known at the time already that in Duchenne, pulmonary function starts to decline around 10 years of age. And then it's a pretty much linear decline up to around 20 years of age when these patients have to go on assisted ventilation, which is, of course, a big milestone in the study. And then the pulmonary function plateaus and they go on assisted ventilation. So the DELOS trial was specifically designed and recruited patients from this age range, 10 to 10, it was actually 10 to 18. And it excluded, of course, patients who needed assisted ventilation. And this, I think, it also provides a nice example that we can learn from later on, because it's a clear milestone. And there are methods to show that if you reduce this rate of decline, it has been shown to be about 5 to 6% per year. You can reduce this by a certain number, then you can push back the milestone by a certain time. And if you figure out this relation, you have a very good chance to justify, to illustrate and justify the relevance of your effect. So that's something we should keep in mind. Look, take a milestone, push it back, and justify your effect by that. That's the second message I want to give on this slide. So the result looked actually like this. The COA, the outcome measure, was peak expiratory flow. It's actually a normalized flow because these patients grow, so you need to normalize it to body size. And the endpoint was change at week 52. So the change at the last visit. And as you can see, this was significant, and the study met its primary endpoint. The primary analysis was a mixed model for repeated measures. That's pretty much the standard method today, or it was at that time already. And time in this model is actually used as a fixed factor, and the covariance structure is unstructured, so it doesn't really matter at which time it occurs. What matters is that to assess the treatment effect, you look at the last visit, usually. So it was the last visit in this study. It can be an earlier visit in other studies, but usually it's you want to look at the difference after the last time point you measure. There is an alternative or an additional sensitivity analysis that we did based on the same methodology, but in this one we looked at all changes basically, not specifically at the last visit. And that's, of course, that analysis has a different justification, but it takes into account a little bit the development of the treatment effect over time. And I'm showing this analysis because in a way it's between the typical MMRM models that we use and the slope models that I'm coming at now. So what the slope method analysis does is under the hood is actually quite simple. You just put a regression line through all the observations you have from a subject, and in the end you average those and compare your group slopes. That's it. What's important to recognize is that, of course, this reduces the degrees of freedom, or it reduces the number of observations, and it becomes a much more powerful analysis usually. So as I said, what you do is you average the slopes of every individual, and you come up with group slopes. And your final analysis, you don't compare it at the last visit, but you compare the differences in slope. And I think this slide is redundant. I've said this all already. So it's important to recognize that these are both linear models. If an outcome measure is not linear, then the model is not the one to use. And now, if the slope analysis has few degrees of freedom and it's so much more powerful, then what's actually the catch? Why doesn't everyone use it? And the catch is quite simple. It's the shape of the curve. You have to, of course, predefine in all the studies your primary endpoint, and then the development of these effects over time often is just not predictable. You don't know where it starts. You always think you know because you have an idea about natural history and other things of the disease. But it turns out that most people shy away from that. Even if it's supposed to be linear, like we were thinking in DELOS, we did not make it the primary analysis. And of course, you have the placebo response, especially in the ataxia COAs, as we will see. Now, to compare directly the analysis, let's look at the numbers. So the primary outcome was, as I said, that the difference in changes from baseline at week 52, and it was about 6.3%. So it's a percentual scale, as I said. And the treatment group stayed almost constant and then declined just a little bit in the last visit, and it was about 2.5 points overall. And the placebo group declined by about 8 points. Quite unexpectedly, that decline was already found earlier, and then it plateaus until the end of the study. So if you look at the other visits, you can see that already at week 26, we had a significant difference, then a similar result at week 39, and then a little bit lower result at week 52 due to the decline in the treatment group. And that's why if you look at the combined analysis or the overall analysis, where you say 13 weeks to 52 weeks, basically all changes, the difference was slightly higher, but because you have many more observations now in the contrast, you have a much better p-value. And now you will see how this leads to the slope analysis, where you in essence look at the group slopes, which should have a similar power to this analysis. But you also see that the shape of the curve is actually quite different, and the slope doesn't really represent what's going on there. Because you kind of disregard this part of the area under the curve, the treatment difference in the slope analysis was 10–15% less. But still, since the analysis is so powerful, the p-value is just about the same range. So the additional power of the analysis brought the p-value into a similar range, despite a low treatment effect. And now I think you can all imagine what would happen if you go to a trial in the ataxias, like the only one successful that we have seen so far, which was the MOXIE Part 2 study. And I don't have the data of this study, so I can't run the slope analysis, but you can imagine if you put a slope for all the visits here and for all the visits there, then probably the treatment effect would be quite a bit less than it turned out to be in that study. The good news here is that the mFARS, or what they also showed is that a subsection of the mFARS, which only looks at the axial components of the score, shows pretty much no placebo effect and a natural decline slope in the placebo group. So this analysis probably would benefit a lot if you use actually the slope over 48 weeks in this case. And that's pretty much it. So the problem is you don't know how your data will look and how the groups will progress, and also how the treatment effect, when it will kick in. And that's why it's really difficult to use a slope analysis in clinical trials. So now I want to switch gears a little and come to my main area of expertise, I think, which is natural history studies. So we have to recognize that they happen in a completely different timely context. And that's, of course, obvious to most of you, or to probably all of you. We look at, instead of looking at just, well, I'd say a maximum of about 2 years in clinical trials, we look at the disease evolution over decades and all stages. And it turns out that in this short period of time, it's quite challenging to show the influence of predictors. And that's why we have natural history studies, where these come out more easily. And an additional point that we, of course, want to pursue here is we want to investigate how do our COAs behave over these long periods of time, and are they actually progressing linearly? And I will say that clinical trials is, of course, an area of inferential statistics. That's where we want to show our effects statistically. But I see it a little bit in a natural history context differently, because that to me is more like a data science task we actually do. And with the big studies that we have in some diseases, the p-values become at least less important, I would say. So to get this a bit more hands-on, I want to show you some data that I've worked on. This is some mFARS values in the FACOM study. We're approaching about 6,000 observations, so that's really big, 6,000 patient years in with ataxia. And if I just show you the bare scores, then there is not much to see. It's just, they're basically everywhere. There's not really a trend over time. You can see that we have a little bit more in the younger patients and a little bit less in milder, older patients. But it's really difficult to see a trend without looking at actually the relevant subgroups. And that happens when you look at age of onset groups. Now, if we look at the averages here over time, you can see that the disease, or the means, not going to say the disease, but the means in the mFARS increase quite quickly then, and then they level off. And of course, that is what happens when you work with a clinical rating scale. The scores get maxed out at some point, and then they reach their ceiling. And a second thing that we see here is also quite typical for these natural history studies, when you have, of course, the patients that will stay longest in the study, and early onset patients that can still come to the study at 40 or 45 years of age are obviously the mild ones in that subgroup. And that will lead to this kind of follow-up bias. Now, if you look at the other groups, you see a similar shaped curve in typical onset FA. And then what happens is, in intermediate onset, this is rather linear. So I wonder if this really is the same curve than that one, but that's a question to be answered. And in late onset, that we have very few in the early ages here. That's why you have this kind of hiccup in the curve. But I think this is also more of a linear curve, like the intermediate onset. So now I want to zoom into a smaller box here and look at some individual curves. And then what we initially did is we did just linear regression. And that's, of course, a very bad representation of the data. The next step then is to do random coefficients, where each individual basically gets their own curve. And what you can see, of course, is that there is an important milestone here in all these rating scale analysis. Oh, I'm sorry. And you see that in the ambulatory phase of the disease, the slopes are much steeper, while in the non-ambulatory phase, they're much less steep. So we need to take that into account, otherwise we represent the data in the wrong way. And now we do random coefficient regression models. You don't really have to go through these details. And the result is, as expected, we see much higher progression rates in ambulatory patients. That's these solid bars here, versus non-ambulatory patients. That's the more transparent bars here. And that effect becomes smaller with milder patient groups, which might indicate that actually these lines that we looked at a few slides before are more linear, and that in earlier onset patients or more severely affected patients, this kind of kink in the curve at loss of ambulation might be a bit milder, or a bit more extreme in early onset, this way around. And of course, if you look at the axial part, that's the second endpoint I showed you from the MOXIE trial. You see that these bars make up, if you compare it to those, most of the decline that you see in ambulatory patients. It's a little bit, the exception is a little bit the very early ones that also decline in upper limb function, but that's a different story. So now what does this mean? We found out that the genetic severity, age of onset group, is really important, but that's also a really subjective parameter, really difficult, and usually companies shy away from using it in the study, because you will always have patients where that parameter is unclear. So what's the significance now? The significance for clinical trials, and now we need to go back to a short-term context, not long-term natural history context, but short-term clinical trial context. And how is a clinical trial done? Well, the first thing is you look at the age that you want to recruit from, that you want to recruit your sample from. And this graph shows the number of observations we have in the FA-COM study, and I'm separating ambulatory from non-ambulatory patients by age. Now imagine you pick a sample from a certain age group, and this is 16 to 24. You can see that this group is dominated by typical onset patients that decline at a certain rate. And there's a few ambulatory early onset patients and a few intermediate onset patients. Now compare that to this group, and it's quite obvious that this one will have an overall lower rate of change because you have more milder patients. Now it's important to recognize that, of course, a patient doesn't start declining less once he crosses that age line. It's really just the composition of patients that is milder in these age brackets. And that's the reason why different age groups in Friedreich's ataxia, and we're now, of course, looking only at ambulatory patients, have different rates of decline. And that kind of age-based context is really important to understand and eventually to stratify by in clinical trials in FA, because it gets even worse or more extreme in children and adolescents. And then if you look at patients younger than 8 years, the question is the outcome measure really still working in them? But the change is certainly even bigger. While there, other effects also play in that I don't really want to talk about. But as you see, if we want to go back to the clinical trial context, we need to go back to changes from baseline, or in this case, the average 1 year changes that are produced in this certain age bracket. Now, once you have done this, you can do that for all kinds of outcome measures that we have. And these are the typical ones that you have seen, those two so far. the upright stability, then we have the ADLs and the time test and so forth. And now, based on the change analysis, we can look at the sensitivity of our measures and see how they work in this context. A little bit off topic here, but I want to mention it because it was a big finding in this study. The upper limb portion, which is this box here, really only declines in really young children. And that's this additional effect that we see in children less than 8 years and a little bit in children 8 to 11 years. But the important part is they do not decline anymore in ages later than that. Well, of course, it's an average, so there are patients who decline, but others catch up due to potentially all sorts of effects. And as I said, now you can look at sensitivity of outcome measures and all these kinds of things when you just put it in the right context. And I'm already done. So I have a very brief summary slide. Slope models are most useful when you look at long-term effects to understand the big natural history studies that we have. So you can look at disease progression, behavior of COAs, influence of covariates, all sorts of things. They're unfortunately sensitive to nonlinear shapes of the curve in clinical trials, and that's why some studies shy away of using it. But then you need to take what you learn from the slope models back to the short-term change models and understand the variability and change, potentially sensitivity, and so forth. And as far as I have seen, these genetic modifiers that are really important in the long-term analysis usually turn out a lot less important in the change models. That's my perspective on things. So with that, I give it back, I guess, to you, Matthis.
Yeah, thank you very much, Christina. That was really interviewing because I think there were tons of questions. So first of all, thanks because you were really doing an excellent job in highlighting, illustrating each specific problem, but also the changes on the findings. So I really like this quite a bit. So maybe just to get the discussion started, maybe we start off with the first part of your talk. Maybe we structure this a little bit, and I'm happy to. I think we should maybe just also start off with questions of understanding. And please feel free, everybody of you. It's if you have just maybe a question of understanding, just something where you want Krista to dig back into it, where you got lost, please go ahead and ask your questions about that. Either to part 1 or part 2, that doesn't matter. So
this is great. I love this format. Quick question on the area under the curve. It looks like that would work well in both cases and better than changing the endpoint. Maybe I missed that, but it seemed like that was kind of best of both worlds. Is it not? What's the downside of the area under the curve approach, where you're really looking at the cumulative differences across time?
It's not really. I'm trying to flip my slides back. It doesn't really work. Where do I have it? Of course, it's the same issue, right? If you have the slope of this curve works the other way around, so it would just separate from the treat groups. The placebo group would just separate from the treatment group. Yeah, I'm having a bit of a technical issue here. 1 second. I was trying to say that if the placebo group deviates from the treatment group very early on, then you have the same problem in this model. It's also quite difficult to justify, I would say, because of course the treatment effect has to build up, and you want to say, you want to measure the biggest treatment effect, and that's usually at the last visit if there is one. The difference is just the slope model looks basically at a rate, and this one just looks at a change.
So if, just so I can make sure I understand, maybe the others understand, the problem with that cumulative change is it's less power statistically than comparing what happens then typically. Is that true?
Yes.
Okay, but it is fine if the shapes are different. That's okay.
Imagine this would be, the placebo group would have behaved as we would have expected to behave by natural history, right? Straight slope down. So if you look at the right side of the,
give us a minute. Yeah, no, it's up. Thank you.
The right graph. Obviously, if the placebo group deviates from the treated group due to a treatment effect earlier than or later than 3 months, let's say they stay the same until 6 months, then in this area under the curve analysis, you have exactly the same problem like the slope analysis. the differences overall become smaller, and you lose the power again. So as long as you're
talking about a different case than what you're showing. You're talking about if it was basically convex instead of concave. Is that right?
Yeah. If it was the other way around here, we would never show this analysis, right? Because then it would speak against us. The effect would be much smaller.
And it's because you'd have more variability, because you'd still have a cumulative difference between
them. No, I have
them.
less difference. I have less difference. See, my pointer works again here. Imagine that placebo point would be here. You would lose that difference here in this analysis. It's the same with the slope analysis. If the shape of your curve works against you, you will have a lot smaller effect.
I think I understand. Okay.
Yes, Gillian.
Thank you, Christian. So I have a question about how you handle the contributions of individuals. So in the slope analysis, you calculate the slope per individual, and then so everyone contributes essentially one slope, and then you average them. In the shape analysis, for example, or change analysis, when you are dealing with this big population data with MFARS, you clearly have some people who contribute, I don't know, 2 data points, some 5, some 1. So how do you handle that? How do you take that into account, the different number of data point contributions of individuals? I don't know if that's clear.
Yeah, I think I know what you mean, of course. And this is something you could discuss. Of course, an individual, if it can contribute to more than one of these bars, and one individual can contribute more than one observation to one bar, right? And in both ways, in both cases, you can handle it using mixed models. If you do that, and that's what I've done, of course, you do sensitivity analysis and check if that kind of leads to deviations in your data. Then you look at only the first observation per age bin, and you see how far off these are. But I think all these statistical points, they're probably more important in a clinical trial context than they are here in this natural history study, because here we really try to see the kind of the broad patterns in the data. And this is what certainly these graphs represent. In the slope model in the clinical trial that I've showed, go back to it. Of course, the response variable in this case is the change, and each patient contributes a maximum of 4 changes. And in this case, the response variable is the slope, only one slope subject. And that reduces, as I said, the number of degrees of freedom. Of course, the model has ways to also deal with more than one observation in a patient. It's not exactly the same if a patient contributes 4 data points or only 2, but that then becomes a discussion on missing data. And it's probably not one for you.
Thank you, Gillian. Did this answer your question?
I think so.
Okay, Gilbert. Gilbert, if you want to go next.
You're on mute.
All right, apologies, I was on mute. Excellent presentation, Christian. I really appreciate it. I'm, attracted to the, the sort of the linear, the individual patient regression approach, the simple linear model. But obviously, as you've shown, first of all, there's the dichotomy between what one sees in natural history and what one can expect in a clinical trial, because of the filter, the entry criteria that apply to the clinical trial that may or may not make it representative of the natural history. That's one challenge. But your example, from the DELOS trial really shows the dichotomy there, because in this case, you've got a treatment effect that's kind of linear, but sorry, I got a spam call. Yeah, you got a treatment effect that's linear, and then, but also on the placebo arm, you got a nonlinear response, which has probably to do with some of the issues with regard to placebo response. In this case, there was a decline that followed more stability. So the linear model in this case, I think the linear fit of individual patients, it's a little bit conservative, right? Yeah, well, that's interesting. That's right.
It is conservative. Yeah, of course.
Yeah, it is. And so the week 13 to 52, obviously, which you anticipated, there would be more bang for the buck, so to speak, acknowledging that treatments take time to develop, an effect. That certainly makes sense. But what about if you had done some kind of simple, like you said, mixed measures, mixed models repeated measures analysis that took into account the entire observation period from time, basically from the 0 all the way out to 52 weeks? Would that have shown? That's probably would have shown less of a difference, right?
I think isn't that what this analysis shows? This shows just all observations.
13 to 52. Yeah.
All the data. So it's this analysis.
So is that compared
I want to say that we have no clue why this curve looked like that.
Yeah, exactly.
It was not an exactly big study. It had like 35 patients a group. And we discussed this for a long time also with the authorities, and no one ever could come up with a good explanation for that. So,
and herein lies, when we issued the press release for the SCA trial, there was an observation of an effect within SCA3, but what was a bit counterintuitive was a lack of placebo response in SCA1 and 2, and that was documented in our press release at Biohaven. And it really, we're struggling a bit in terms of identifying, trying to explain why that happened. You're right about the issue of you're spot on when it comes to trying to predict these trajectories based on age of onset or time since symptom onset. The challenge is that predictors that might work very robustly in a natural history design by larger sample, etc., may not work as well in a trial-based multivariate analysis, because you don't have the numbers and you don't necessarily have the representation of these predictors in a clinical trial, which is always kind of an extracted, it's a filtered population, so to speak. So
yeah,
it is a bit of a bit of a challenge. But I think that the approach that you described, where there was an anticipated nonlinearity and you did linear regression, is sort of a phased linear regression, right? So the first phase was one linear regression, and the second phase was a second linear regression. I can't remember which graph that was, but obviously you had different slope. Yeah, I think it's that one. So that's attractive, because I think it does permit it's a slope analysis that is a little bit conditional on the observed data. So, and I don't know, when you're submitting these types of analytic plans to the regulator, everything kind of has to be pre-specified. But wouldn't it be good to build in a conditional type of analysis where, okay, if it's pure, if the observed data is linear in nature or fits kind of a linear trend, that's what we go with. But if we see a more complex pattern, as you've done here, where you essentially have it's non-linear, but two linear regressions fit the data actually quite well, right? To kind of have that as a conditional secondary analysis, if in fact one does not observe what you expect to observe in the trial, so there's really this, I think this approach as well shows a little bit of flexibility. The question always is how do you convince the regulators to have, specified conditional analyses in the event that what we see is not what we expect to see, especially on the placebo arm, right? The untreated arm, you should be able to anticipate that trajectory, but sometimes you don't. And I think what's interesting, this incites a bit of thought about how best to really have these discussions with regulators and say, look, there's there's some fluidity here that we really can't fully anticipate. And we like to have the opportunity to do more flexible analyses. So anyway.
Well, that's of course not, this one is of course an analysis in the context of the natural history. That's not a clinical.
Exactly. Yeah.
And I'm just suggesting that there needs to be some limitation in enrollment, which de facto everyone does. Right?
Yeah.
If patients cannot do a certain walking tests, or in the RIADA study, it was the exercise test, these kind of things, if they cannot perform that anymore, it's basically the functional limit that you give to your patients so they have room to decline. But what you describe is the trouble that you have then with clinical trials, as you have seen it in your trial. And that flexibility is not on the horizon. We'll just have to live with it.
Yeah, one of the other observations I think you had from Friedreich's ataxia, I think the paper that was just published, I know that I can't remember the context, but it was a paper looking at the difference between longitudinal modeling distance between axial and appendicular SARA scores, and clearly there, that observation was consistent with what we found in our first trial, that the appendicular items were not it did not seem to change over time. We're not sensitive to change over time, whereas the axial items were actually much more sensitive to longitudinal change, which is why, and that was based on those input from the regulators. Well, we went from total SARA to kind of a modified SARA that focused solely on the axial items and did not include the appendicular items. So yeah, and that's consistent.
Thank you, George. Just looking a little bit at the time, and others have raised their hands. So
sorry.
I think I don't know the short answer to this. Christian, still, otherwise we hand on to Rebecca.
No, I think it's fine. I don't see really.
There was more comment, right? Yeah, Rebecca.
Yeah, sorry to be too verbose.
Fine with me, yeah.
Thanks a lot, Christian, for that fantastic talk. I wanted to come back to exactly that slide, so your mean change by age group analysis. So if you look at those outcomes, most of them tend to get smaller. The changes tend to get smaller in older age groups, and you attribute this mostly to the different composition of these age groups, with more milder patients in this age group. But at the same time, older age is associated with a more severe disease. So if those items have a ceiling effect, it would occur exactly in those older age groups. Is there a way to figure out what the contribution of the different composition of this age group versus a problem of the scale or the outcome in terms of a ceiling effect would be?
I mean, the idea to separate non-ambulatory from ambulatory patients is simply the ceiling effect in the axial scores. After that, we have nothing to measure anymore. And what happens actually that you can't see here in non-ambulatory patients is that they start to decline in the far speed, right? So that happens after loss of ambulation, and it also happens with a variability that is far away from anything useful in a clinical trial. So what I'm suggesting, in essence, I just call it ambulatory, but what there really has to be is an upper functional limit, as I think you indicated, that kind of gives these patients room for decline. If that's ambulation, or like I said, exercise test, or even stricter criteria on balance, maybe, to give them more room to decline. These differences in the ambulatory and non-ambulatory phase that you've seen in this slide, they are not necessarily true depending on the population. So late ambulatory will probably change very similar to earlier non-ambulatory if you look at the whole SARA score. But then again, you mix two functional things. One of them is walking, the other one is upper limb function, and then you have probably more issues again justifying any effect you would see. So yeah, well, no, I think I went off from answering your question.
Yeah, but thanks, that was helpful.
But maybe just to follow up one more from Rebecca's remark. So you would go to, in order to correct for the ceiling effect, to take ambulatory versus non-ambulatory. Is there a way to do this in a more fine-grained, non-dichotomous fashion? Would it be able to do it via stratification of the MFAR score itself and take it as a covariate? And you know what I mean? And just and integrate it into the model rather than having this coarse grade.
That's something I didn't mention, but of course the baseline is always a covariate in these models. It has to be in all scales, because the lower the scores are, the more people will decline anyway. So you need the baseline as a covariate. There's no way around that, and there's nothing wrong with it. It's in most of the clinical trials on any outcome measures. This is usually done. If you want to more fine grain the mFARS or the FARS upright stability score, then you need to change the score, and I think that's possible. But then we're looking at a different outcome that we have no experience with. Yeah, the SARA, for example, might be more sensitive in that range because the stance items are tested in a different way. But I don't want to wander off down to other topics.
So maybe this is something that Sophie will tell us in her talk.
Yeah.
Yes, you're next.
Thanks, Christian, for this wonderful talk. I was wondering, one reason why we perform these natural history studies and create these elaborate slope models is, of course, find stratifiers and predictors. Another reason is that we think they can help us in telling us the sample size we need. How would you put these models in the context of sample size estimation? I mean, using a change model, if I understand you correctly, is a way to avoid the unknown shape of a potential response curve or of the curve of the placebo group. But still, is there anything else than leaving a safety margin to this change prediction, which is as precise as possible given the most detailed subgroup analysis you can make?
So I think the first question I can answer, the sensitivity that we see in these outcomes from natural history studies, the last graph that I showed and didn't talk about much, they have their value in the context of the natural history study and maybe in comparing the outcome measures. How we will actually power the studies, they have basically nothing to do with it, because the changes in the study will be very different from the changes that we see in the natural history. Now, the second part of the question, I'm not quite sure I understood that right. It's maybe similar to what Matthis tried to say, that there's really nothing to do once these reach the ceiling, then you can't use them anymore in the population. Or maybe you want to repeat the second part. I didn't quite get it.
I mean, what you get from you have a data set and you do the short-term analysis, which gives you a change of the score in a trial reasonable time frame of, let's say, 1 year.
Yeah.
And what you do if you use a change model is to say, okay, with this type of analysis, I know I am avoiding potential detrimental effects of unknown response curves that could be detrimental to analysis with other methods. But still, there's how do you do you include placebo effects? So you have a rule of thumb approach. Do you include placebo effects? So you think, okay, it's impossible to predict the shape of the curve anyway. So this is the best method to go. Let's work with this change score. Let's look at it parametrically. We have a distribution of changes, and then let's do a classical statistical analysis and see whether we get 80% power. And so no reason for any more elaborate methods here.
So in the natural history analysis, I don't think there are more elaborate methods. And of course, the reason why you don't know the shape of the curve is that you don't know when the effect of the drug will overcome, or the natural history decline will overcome the effect of the drug on the placebo effect, right? So this is obviously placebo effect, or part of it is placebo effect. And then the natural decline kicks in and they wander off. There's probably no way to predict when that will happen. And I will say, imagine you could do a slope analysis starting at week 12. Okay, you can say, okay, I know exactly that my placebo effect will be gone after 12 weeks, 24 weeks, so I'm just putting a slope through the rest of the curve. And this is an exact analysis that I have discussed with the FDA, and they've pretty clearly said no, because it doesn't cover the totality of the data. And yeah, it was a big discussion a long time ago, but we were not allowed to do it. So I think with these endpoints that will be prone to placebo effect, we're just stuck where we are.
Maybe if I've got you right, Andreas, is the question from Andreas is you come up with a sample size estimation by using natural history data and let's say change models, and then, but for example, add a certain safety margin. For example, add a safety margin of assuming a placebo response of plus minus 20% of change, or whatever this is. Maybe you know it from a related condition, what rate of placebo is in general to be expected. Then you add the safety margin to your modeling for your sample size calculation. Would that work? And this would still then allow you to build all your calculations and modeling on the natural history data.
So these effect sizes or group sizes that we calculate from natural history studies, these are among the most simple analysis that you could do. It's basically mean and standard deviation, that's it. And if I add a safety margin to my mean, I have no clue where I should take that from.
Mm-hmm.
Right? We don't have enough experience. I mean, if you have a field that I've been working in, like Parkinson's, that you have 100 studies that have been run, we know exactly the change, we know exactly the
yeah.
That's it. If we had 20 studies like MOXIE, then
no, that's true.
We don't. Mm-hmm. And we won't have it for a long time.
Yeah.
Yeah.
Thank you. Jen Farmer.
Thank you. I just had two maybe follow-up questions, comments. One was directly related to this discussion about the placebo effect in FA, and Christian, the data that is available to maybe start to understand that better. I mean, we don't have 100 trials, but you know, we have 4 or 5. They have not all run as long as MOXIE. Some have been shorter, but there is a remarkable consistency in terms of this effect and how long it lasts before natural history takes over. So, you know, it does seem like we should be getting closer to being able to do that, right?
We do, yeah, definitely. But still the context is different for each of these studies, and I think I was just trying to say
sure,
the amount of experience. Of course, yeah, I agree with you.
You know, because the idebenone studies and the EPI studies, this study, interferon gamma, like when you compare if you were to look across all of them and just look at the mFARS over time, like it's remarkably similar what happens with that placebo group.
Yeah.
And
but
then
still,
I guess,
this is more. I don't want to contradict you, but it's basically more. We have an idea when the natural progression of the disease will overcome the placebo effect and they cross the 0 this time. Seems to be very similar in all the studies, but we're far away from knowing standard deviations and effects as we do, like I was bringing up the example of PD.
Gotcha. Okay, thank you. That was helpful for me to understand further. And then Rebecca's comment, if you go back to that slide you had up about the change by age group, I think you're exactly right that especially in a disease like FA, one of the challenges we have is related to the heterogeneity. And so I do think that the people that are out in the 25 plus group, maybe even the people, you know, even a little closer into age 20, who are still ambulatory, are very, very different than the people who are in the 8 to 15-year-old range, right? So it makes sense that some of these measures are just going to be more sensitive in different populations within the disease, and that's part of what I think this shows.
Yeah, and of course, looking at the numbers like this, and then behind that, know how these patients look like in their daily life and how they perform these measures. That's another question, right? Completely agree.
Thank you. I think there was also more to comment. Rebecca.
I wanted to come back once more to the sample size challenge. So could you elaborate a little more about the reasons why you think natural history data is not suitable for sample size calculations. I understood the aspect of the placebo effects. Are there other reasons? That's one part. And the other thing is, if we can't use natural history data, what else can we do if we run the first clinical trial in a rare disease?
Well, it's just very obvious that the standard deviations we find in clinical trials is much lower than we see in natural history studies. And that's, of course, I mean, there might be many reasons, but one of them is that, of course, you monitor them more closely. If you bring them in every 3 months, they will stay much closer to the procedure, to the trial, and probably behave much more consistently than when you see them once a year. And of course, in the natural history trial, you have all sorts of people. You have people that think I'm participating in a study, and others that just come every couple of years. And I think that diversity in the behavior is one big factor. And I'm not saying these calculations are useless. It's just they are very useful to compare the sensitivity of the scale within the natural history. But I'm trying to remember the standard deviation that is in the READA protocol, and I think that protocol is public. And I think they used a standard deviation of about 4 to power their study. And what we see in the natural history study is more like 10 or 11. So it's just much, much bigger. It's way off. And that's why I'm saying to power the studies, look at older historical data is much more useful. And it also doesn't really make a difference if we say we're not only looking at one visit, or we're looking at repeated visits, and then reduce the standard deviation a little bit. That's just numbers game. I wonder, I also don't remember what the standard deviation was in the actual trial at READA, but these numbers are what we need to use. And maybe we can make a relative comparison. You see, if in this age group it was like twice the standard deviation from the natural history, or half, then we can maybe predict from that to other age groups. But other than that, there is not much we can do.
Christian, this is Minghua. I'd like to ask, when you say these natural history standard deviation higher than the clinical trial, which is, we commonly see that, right? But is this the raw standard deviation or the model? Like, you could also fit an MMRM model, adjust for covariates to the population, that maybe then like do some adjustment to the population that you need, and would that reduce the standard deviation closer to clinical trial? Or I think it's probably also another aspect might be the quality of the clinical trial is also much better, right, than a natural history study. That cannot be overcome by the modeling piece.
Well, you could make the natural history much more expensive, yeah, of course.
But do you think the modeling piece would help get the standard deviation? Do you know what I mean? Like get it closer, more. Yeah. Yeah.
Would you really trust that more than common experience from a trial?
If you have enough data from a trial, I would trust more from the trial.
I would ask Gil what the standard deviation was and use something close to that.
I see.
That's much easier than trying to model it from the natural history.
I see. Thank you. Yeah, I'm not familiar, super familiar with this disease area. Still trying to learn.
Experience is really what will teach us in this case.
Yeah. Thank you so much. Your talk is really enlightening.
Thank you. I think we have time for one more question. Andreas.
Thanks. I'm just questioning what we do in this natural history trials all the time. One reason is that we also like to simulate study designs with multiple visits. So we think we add visits to the model, and then we can lower the sample size to handle rare diseases. So if you use a change model, you would say, if I don't want to be liable to odd curve shapes, you pick one endpoint after 1 year, and then this is your primary endpoint. So in your model, there would be no use of adding additional interim visits, right? So you would only analyze one visit, endpoint visit, and you can skip all others, unless you would have some possibility to do some conditional analysis where you could use information gathered at interim analysis to guide further analysis.
So now this becomes a little bit detailed on statistics. So the primary analysis in DELOS, which is the example we were talking about, is the change from baseline at week 52, or the difference in that, in the change. In this model, of course, all the other changes contribute to the difference. It's just what you look at is the contrast at the last visit. So that's, now how far do we want to go down that rabbit hole? But all the other, what we did earlier, maybe that's a good comparison. What we did earlier is every patient who dropped out, we used LOCF. We carried forward that value to the last visit and let it contribute to the mean. And now it's statistically been shown that that's not a very good idea because it inflates the type 1 error. You get a lot of, you become prone to type 1 error, basically. And what these models now do is they use all the changes, just they have the visit treatment interaction in the model. Now it becomes statistical. And you just look at the contrast of the last visit. So all these changes contribute, also the dropouts contribute. And it modifies slightly the change here, so that you can actually look at in the result. The other question in natural history studies, I think the main benefit from adding more interim visits is that people will adhere to the study better than they do otherwise. But maybe then you get a bias and you have more people that are just more motivated to contribute to that study. Again, I don't believe in sophisticated methods to reduce variability in large natural history studies. I mean, we have another natural history study that's not been published. It's called FA Child. People are seen every 6 months instead of every 6 years. Every year, sorry, not 6 years. And there we can clearly see people adhere better to the procedures of the study and the variability goes down. And then if in addition we add the interim visits, our confidence intervals, again, they become smaller. So there's two parts of it. One is that the patients adhere better to the study. I think that's what the reason. And the second one is the statistical addition of these additional visits. You can separate these two clearly.
And Christian, can you give us just, it's hard for me to say in general, but can you give us a feeling by how much is added by adding a visit? So you statistically, what is the effect size that is expected to be improved by adding a visit? So, or how much of the noise is expected to be reduced? Can you model this and can you quantify this?
I can come back to you on this.
Because I think that's the crucial question also that Andreas is going to have is if we add one visit or 2 visits, how much does it improve? Yeah.
I mean, in the clinical trial, there this becomes much more powerful, of course, if you see them more often. That's why we call it repeated measures.
Yeah.
All these measures are added into the model and they add observations.